Alright, welcome to Physics Online. Here we go. We got a circular motion problem. This is very traditional, where we have a bucket of water with a mass of 20 kilograms. It is spun around a vertical circle, so we'll talk what that means in a sec. If the bucket is spun with a velocity of 15 meters per second, and the radius of the string being swung is 4 meters, that's my radius, answer the following questions. So we're going to kind of use this to break down a bunch of different circular motion principles. And I'm not going to cover every single one, but this should get a good smattering. So first, we're going to look into the period of rotation. So fundamentally, we're looking for what is t. All right, big old capital T. So here I have a person standing on a platform, because the only way you're getting a 4-meter radius swing, because that's like 12 plus feet, is if you're standing on a giant platform. So just to emphasize this, let's have this. We've got string, and then bucket, spinning, circle. Alright, so we're spinning this thing in a circle like so. Alright, so if we want to figure out what's the period, then we're going to be needing to break down what it is we actually know. So if I make a list of my givens, I know that the radius is 4 meters, and I know the speed at which we're swinging this is 15 meters per second. The mass is 20 kilograms. And so if I look at all this information, I'm saying like, hey man, what's the period? So I like to put that, like, what is this period? Mass doesn't really matter, but I've got V, R, and T. And the equation that's going to help us get there is this guy. So my speed is equal to distance over time, but since the circle, my distance is 2 pi r, and my time is that very specific time, which is the period of rotation, capital T. So now if I take this information, I substitute it in where it belongs, I get 15 equals 2 pi times 4 for my radius, divided by t. And so now all that's left is algebra. Now it's got fractions in it, so some people make some algebraic mistakes. So, solve this first, pause right now, solve it, and see if you get the same answer I do. If you do your algebra correctly, you should get the period is equal to 1.676 seconds. Alright, so that's the period of rotation. That's the exact amount of time it's going to take to make one full rotation around this crazy circle here. So that's our first question. The second question, so let's change colors here, no question, is what's the force of tension? So we're looking for F of t in this one. Well, if we're looking for forces, got to draw ourselves a nice force diagram. So let's do that. So we've got a 20 kilogram bucket, and again, we are spinning a circle over our head, so it's perfectly vertical. So we've got this going on here. And then, if I look, this is the top. Alright, so again, I'm looking at like the very max peak of this. So at the top of the string, if we were to do our forces, we've got force of gravity pulling us down. And we've got the string also pulling us down. That's tension. And I put a little dot here just to show where's the center of my circle. So when I go to solve this, I use my old friend net force equation. So sum the forces towards the center of the circle equals MAC. So I'm just going to add up all the forces I see that are in this plane that cuts through the center of a circle. So I've got a negative mg, and I've got a negative force of tension equals MAC. Now, here's the thing. Acceleration has a direction too. So we want to make sure we at least note this, because there's some people make some mistakes. So centripetal acceleration always points towards the center also, which happens to be down. So when we do the math in this case, we're going to be seeing, that's right, negatives. Good call. So I'm going to do some replacement here, and I'm just going to make this whole thing negative, because anything times a negative is a negative. So I've got a negative, and I'm going to replace AC with v squared over r, because I've been given my speed and I've been given my radius. So it makes sense. So now it's a matter of substitution. So negative 20 times 9.8 minus the unknown force of tension equals negative 20 times, and then we've got v squared, so that's 15 squared, all over my radius of 4. All right, if I do all this work, crunch all my numbers, I get that the force of tension in the string is actually 929 newtons, which is really freaking large. This would be one heavy bucket. Fun fact, Mr. Szymanski has a weight of just over 1,000 newtons. So maybe it's like 1,200. Whatever. This is like you spinning or lifting Mr. Szymanski. So that'd be kind of hard stuff to do. But hey, like I said, play a circus act, play a giant strongman. Or woman, no judgments. So now let's answer that last question. Whoa, wrong buttons, wrong buttons, wrong buttons. Where did we go? Whew, deep breaths. Okay, so we're back. I found my page. It disappeared on me there. So last question is, what's the minimum velocity the bucket needs to stay in the circle? All right. So we want to keep it in the bucket so the water does not go splash falling out. And if we look at that, we kind of look at a limit here. So we've got our 20 kilogram bucket, and if the water was to fall out, then that means it's in free fall. So the only force acting on it is the force of gravity. So if we can get this thing so that it's accelerating faster than gravity, then that means that as it falls, we're going to actually catch it constantly. So that's our limit we're looking at. We want to basically outrun gravity. So if we do our net force equation with only gravity, we have C equals MAC, and the only force we have is the force of gravity. And again, we're going to look for that v squared over r, because that's the information we know. Oh, look, mass is gone. Mass is gone. I love when mass cancels out. So we get 9.8 equals v squared divided by 4. If we solve for this, we get a velocity equal to 6.26 meters per second. But like I said, this is kind of our limit. So if we want to make sure that it stays inside the bucket, we don't really want equals to. We want to make sure that we are spinning this faster than. So we're going to bust out that greater than symbol. So we went through, one of our basic kinematics problems of circular motion. We talked about net forces. We talked about some limits. The only thing that we did not emphasize were the application of some of our other equations that we could have done, like we could have solved for acceleration. We never actually solved for it directly. We solved for it indirectly a whole bunch of times. But if we want to know the acceleration by itself, we could use, say, v squared over r. Or, since we know the period of rotation, we could also say the centripetal acceleration is equal to our friend 4 pi squared r over t squared. So we have some choices when we solve these. And that's basically how you're going to solve a good chunk of these. One thing to keep of note of, this was at the top. Okay, so this was for the top. If we were to draw it at the bottom, we would have a completely different force. Totally different scenario because our force diagram is going to look different. So my challenge to you would be to try and solve that one. All right, so to steal something from my good friend Will Wheaton, play more games.